let's take a look at some properties of the cross product. Now, a very important property of the cross product is that A cross B is not equal to B cross A. And I'll talk about that a little bit earlier as to why. And let's just go ahead and try to prove it quickly. First, let's find I cross J. Now, just as a reminder, I equals 1, 0, 0. And J equals 0, 1, 0. So, if I were to draw these on a set of axes, here's my x, here's my y based on the right-hand rule, here's my z. Now, I comes out here, this is vector I, and j comes out here, a distance of 1. This is vector j. Okay, so let's take a look at the cross product of I cross j. Now the angle between these is obviously pi over 2. So the magnitude of I, well, let's just write this out. I cross j is equal to the magnitude of I times the magnitude of j times sine of, in this case, is going to be pi over 2 times the vector n, which is orthogonal to both I and j, based on the right-hand rule. Now, the magnitude of I is going to be 1, times the magnitude of j, which is also 1. Sine of pi over 2 is also 1, times this vector n. And we define this vector n based on the right-hand rule. Now, if I put my fingers, my fingers of my right hand along I and curl them toward j, that only happens if my thumb is pointing up. So that tells me that vector n, I'm going to change colors here, vector n is in this direction. It's up. And n is a unit vector. Now I multiply unit vector by 1s, what I actually get is this vector k. Now I want to do j cross I. Well, j cross I, this is going to be the exact same idea. It's going to be equal to the magnitude of j times the magnitude of I times sine of theta times this vector n, which again, n is a unit vector. Well, again, the magnitude of j and I is both 1, so this would be 1 times sine of pi over 2 times n. Well, this is just 1 times 1 times 1 times n. But remember, the direction of n is going to be identified by the right-hand rule. Now, when I put my fingers on j and try to curl them toward I using my right hand, I can't. The only way to do that is if I curl them back around here. But this is the angle that I need right here. So what this means is I have to turn this thing upside down or turn my hand upside down so that my fingers my fingers run around j and I curl them in, they go toward I. And the only way that'll happen is if this vector n is actually equal to the negative of vector k. So this equals the vector k, and this equals a vector negative k. So A cross B is not equal to B cross A. Okay, let's see here. Let's take a look at a couple of interesting properties here. A cross B is not equal to B cross A. It's actually equal to the negative of B cross A, which we just did with the k and the negative k. A scalar C times the vector A cross vector B is equal to the scalar C times vector A cross B, which is the same as vector A cross the scalar C times vector B. So I can kind of move this scalar around in different ways. A cross B plus C, where A, B, and C are all vectors, is the same as A cross B plus A cross C. It's kind of a distributive sort of a thing here. And A plus B cross C is the same as A cross C plus B cross C. Again, it's sort of a distributive thing going in the other direction. So these are some useful properties that may come in handy when trying to work out some cross products. Now, a very interesting result of the cross product is that it can be used to interpret as the area of a parallelogram defined by the vectors A and B. So let's think about that for a second. I'm going to draw, say, a vector here on B. And vector A. Now, these two define a parallelogram. So if I were to continue this, or basically copy over vector A, it would be like that. Then copy vector B over, it would be something like that. So now I have this parallelogram. And when I look at this, if I take a look at this component right here, with this being theta, this component here is the magnitude of B times sine of theta. And that's the height of this parallelogram. Now remember, the formula for the area of a parallelogram equals the height times the base. And here the height is equal to the magnitude of B times sine theta. And the base is equal to the magnitude of A. So this is actually going to be equal to the magnitude of B times the magnitude of A times sine of theta, which is equal to the magnitude of A cross B, which is equal to the magnitude of B cross A. See, A cross B and B cross A are not the same, but the magnitudes are. If we take a look at that example we did with earlier showing I cross J and J cross I, one was K and the other was negative of K. Well, the magnitude of K and the magnitude of negative K are both 1. So the magnitudes of A cross B is equal to the magnitude of B cross A. Although A cross B by itself is going to be the negative of B cross A, or just the opposite way around. The negative of B cross A is equal to A cross B, however you want to look at it.